In this video, we'll discuss about phase response of FIR filter. Prove that an FIR filter having impulse response with even length and symmetric nature has a linear phase response. Now let h of n is a causal finite duration sequence with n samples, that is n is equal to 0 to n minus 1. That is, let h of n is a causal finite duration sequence with n samples. It means that h of n is having n samples, that is from h of 0 to h of n minus 1. Here h of n is said to be symmetric if it satisfies the condition is h of n is equal to h of n minus 1 minus n. So if the impulse response, that is h of n, satisfies this condition, we can say that h of n is a symmetric sequence. Now if I consider n is equal to even, as I said, h of n consists of n number of samples. Now we'll assume that this n is an even number. That is, let n is even. So now I will show one sequence. So consider that this is h of n sequence. So we'll assume that n is equal to even. So in this case, I will take, say, n is equal to something 8. So this n varies from, this is 0, this is h of 0, this is h of 1, this is h of 2, h of 3, h of 4, h of 5, h of 6 and h of 7. As I said here, n varies from 0 to n minus 1. So if n is equal to 8, then it will vary from 0 to 7. So this h of n sequence is symmetric at this point. We can say that at this point it is symmetric. It means that the samples on right side of this point is same as the samples which are on left side of this point. That is nothing but symmetric. So here, so this point will be, if I consider in general n, this point will be n by 2 minus 1. This point will be n by 2 and this point will be n minus 1 by 2. That is, if we take n is equal to 8, here we can see that n 8 by 2, that is 4 minus 1 is 3. So it is verified. So here we can see that n is equal to 8. 8 by 2 is 4, and this is the point. About this point, h of n is symmetric. That point is n minus 1 by 2. That is, in this case, it is 8 minus 1, 7. 7 by 2 is 3.5. So its value is 3.5. So this is the symmetric property. Now we'll see if this h of n is even length, that is, we have taken n equal to even, and it is symmetric in nature, then definitely it possesses a linear phase response. Now we'll verify whether it possesses linear phase response or not. So now, taking Z transform of h of n. We know that z transform of h of n is represented as h of z is equal to summation n equal to 0 to n minus 1 h of n z power minus n. This is the general formula of Z transform. We'll call it as equation 1. Now, referring this diagram, I will rewrite equation 1 and I will split the summation as h of z is equal to summation. Here we can see that it varies from 0 to n by 2 minus 1. I will take it as n is equal to summation n is equal to 0 to 3, that is nothing but n by 2 minus 1, n by 2 minus 1 h of n z power minus n plus, I will split the summation as, then from 4 to 7, that is n by 2 to, I can say this point is nothing but n minus 1, that is n is equal to n by 2 to n minus 1 h of n z power minus n. Let it be equation 2. So in equation 2, just I have splitted the summation. Instead of taking n equal to 0 to n minus 1, I have splitted into n equal to 0 to n by 2 minus 1, that is this part, and from n by 2 to n minus 1. So now take some other variable m such that m value is equal to n minus 1 minus n. Let some other variable m which is equal to n minus 1 minus n. n minus 1 minus n. Now in equation 2, in this summation, I will make use of m variable instead of n variable, such that, so here I can say, therefore I can write n is equal to n minus 1 and this m will come on right side, that will be m. So here we can see that if I try to replace variable n by m, then we should take care of the limits also. Here n varies from n by 2 to n minus 1. So here n is equal to n by 2. So if I try to replace this with m, in that case I can say for n is equal to n by 2, the m value will be equal to, that is n minus 1. So this n is nothing but n by 2 minus n by 2. In that case its value will become n minus n by 2 is n by 2 minus 1. So similarly the upper limit is n is equal to n minus 1, that is for n is equal to n minus 1, then this m will be equal to n minus 1, this n is equal to n minus 1 minus n plus 1, which is equal to 0. So therefore equation 2, I can say, therefore in equation 2, the second summation is, say, rewritten as, that is h of z is equal to, I will write the first summation as it is, n is equal to 0 to n by 2 minus 1 h of n z power minus n plus summation. So in second summation, instead of using n variable, I will use m, that is m is equal to, so the lower limit is n by 2 minus 1 and the upper limit is m is equal to 0 h of, so here we have h of n, so n should be replaced by n minus 1 minus m into z power minus, so n is again n minus 1 minus m. So I will rewrite this equation as h of z is equal to summation n is equal to 0 to n by 2 minus 1 h of n z power minus n plus, now I will interchange the limit values, that is m is equal to 0 to n by 2 minus 1, which is same as this one, h of n minus 1 minus m z power minus of n minus 1 minus m. I will call it as equation 3. So here, as we know, the variable m is dummy, so instead of using m variable, again I will make use of variable n, that is replace dummy variable m by n in equation 3. Therefore I can rewrite equation 3 as h of z is equal to, first summation I will write it as it is, n is equal to 0 to n by 2 minus 1 h of n z power minus n plus summation, here instead of m I will use n is equal to 0 to n by 2 minus 1 h of, this is capital N minus 1 minus m, I will represent it as n into z power minus n minus 1 minus n. So now here we can see that if h of n is symmetric, then it should satisfy the condition h of n is equal to h of n minus 1 minus n. So here we can find h of n minus 1 minus n. I will replace this is nothing but h of n. So therefore I will rewrite this h of z as h of z is equal to summation n is equal to 0 to n by 2 minus 1 h of n z power minus n plus summation n is equal to 0 to n by 2 minus 1 h of n z power n minus 1 minus n. So therefore I will rewrite this equation as h of z is equal to, here the summation is common, summation n is equal to 0 to n by 2 minus 1 h of n. So here this term and this term, I will h of summation and h of n is common, I can represent the remaining term as, that is z power minus n plus z power minus of n minus 1 minus n. So now to get the frequency response of the digital filter, we should replace z by e power j omega. That is, to get frequency response of the filter, call it as equation 4, replace z is equal to e power j omega in equation 4. So therefore now I can write equation 4 as h of z is e power j omega is equal to summation n is equal to 0 to n by 2 minus 1 h of n. Here we can see that z is nothing but e power minus j omega n plus e power minus j omega. We have n minus 1 minus n. So now to bring it to the standard form, I will rewrite this expression as h of e power j omega is equal to summation n is equal to 0 to n by 2 minus 1 h of n into say e power minus j omega n minus 1 by 2. Now I will represent this term as e power minus j omega n minus 1 by 2 plus e power, that is plus j omega n minus 1 by 2. So that is, if I multiply this term with these terms, I will get back the same expression, that is this one. Now we know that cos theta can be represented in exponential form as e power j theta plus e power minus j theta divided by 2. Here we can see that this term is like e power j theta, this entire term is theta, e power minus j theta. To bring it to standard form, I try to express this in as a cosine function. So I will divide this by 2 as I get this form. Here I will multiply this by 2. It doesn't make any difference. Now we can see that here theta is nothing but this term is the theta and this term is the theta. That is e power j theta, e power minus j theta. Therefore, now I will represent this equation as h of e power j omega is equal to, I'll take this term outside, that is e power minus j omega n minus 1 by 2. The remaining term, that is summation n is equal to 0 to n by 2 minus 1. We have 2h of n into, so this term is nothing but cos theta, that is cos theta is this entire term, that is cos of, we have omega n minus 1 by 2 . So let me call this as equation number 5. Generally we know that h of e power j omega is nothing but h of omega, or I can represent it as in terms of just like polar form, say h r of omega into e power j theta of omega. Now if I compare this expression with equation 5, I can write this is hr of omega and this is e power minus j theta of omega. Therefore I can write it as comparing above expression with equation 5, I can write hr of omega is equal to summation n is equal to 0 to n by 2 minus 1 to h of n cos of cos omega n minus 1 by 2 and theta of omega will be e power minus j theta of omega. So this term is theta of omega. This is nothing but theta of omega. Theta of omega is equal to that is minus omega n minus 1 by minus omega n minus 1 by 2. So this is true if HR of omega is greater than 0 and its value will be omega of n minus 1 by 2 plus pi if HR of omega is less than 0. So now here we can see that theta of omega is nothing but a phase which is equal to minus omega of n minus 1 by 2. Here omega is the variable and n minus 1 by 2 is the constant. So here we can see that theta of omega, where omega is the variable, is equal to minus omega of some constant. It means that it is linear. Therefore FIR is linear phase. Thank you for watching.